This first video focuses on rate of reaction 1 on your mind map. Rate is all about how fast a reaction is proceeding, how quickly it's proceeding. And when we actually want to measure rate, what we're actually doing is we're measuring how much product is made in a fixed time. So it's all about what's being produced. So it could be, for example, a solid that's being produced during a chemical reaction, or it could be a gas that's being produced by a chemical reaction. So the units that we might see for rate will depend on the type of chemical reaction you actually have. So for example, if it's a solid being produced, you might have the unit of grams per second. How many grams of the solid is being produced every single second? Or you might have grams per minute. You don't tend to have grams per hour or anything like that because the values would be probably too big. When it comes to volumes of gas, you tend to see units that are similar, in other words, per second or per minute, but because we're talking about gas volume, we're talking about the number of centimetre cubed of gas produced per second, or the numbers of centimetres cubed of gas being produced per minute. So units are quite important, and being able to see how you can calculate rate from a graph and how you can work out the unit from that graph again is a very important skill. So you may, for example, be given a graph, and let's just say we are talking about volume of gas in centimetres cubed. And along the bottom we have the time, and that time is going to be in minutes. Now most graphs, when you're measuring either mass or volume, will produce a shape like this. Quite a quick start point, and then it will start to slow down until eventually you have made the maximum volume of gas that you could possibly produce, and basically the reaction has stopped. In this particular case, we can actually measure rate. And how we can measure rate, obviously depending on the question, is to look at how much gas is produced over a particular period of time, which goes back to our definition here. How much product is made in a fixed time. So let's say the question asks for what the rate is in the first 2 minutes of this particular reaction. Well, the first thing you do is you find your 2 minutes on your x-axis. You draw a line in the exam using a ruler, please, up to where the line is, and then you draw the line across to the volume. So that will give us a volume produced in 2 minutes. Now let's just say that that volume happens to be 20 centimetres cubed. How do we work out the rate? Well, the rate will be the volume of gas, in this case 20 centimetres cubed, divided by the number of minutes, the time, in this case 2 minutes. When we do that as a nice calculation, it's quite simple because we've got 20 divided by 2, so it works out to be 10. So what would the unit be? Well, the unit is dependent on the units in volume and time. If we have a look at the units along here, we've got things like centimetres cubed per second or centimetres cubed per minute. You look at your volume or your mass unit, and you then per the time unit, in this particular case mins, okay, or minutes. And that gives you the ability to calculate the rate from a graph, but also to work out what the unit would be for that particular example. In this case, 10 centimetres cubed per minute. So when we talk about rate, what we're really talking about is this. Rate is one of two things. It's either the mass of product produced over time, or it's the volume of gas produced divided by time. Depending on which one you're looking at, if we're looking at the mass of product, you are going to have units like this, because gram is the unit of mass. If it's volume of gas, you're going to have units like this, because volume is measured in centimetres cubed. Now, the other part of rate of reaction 1 is starting to look at something called a limiting reactant. Now, all of you will have an idea that during a chemical reaction, you'll usually have, but not in every single case, two reactants, I'll just call A and B, reacting together to produce two or more products. So the products are the things that are made, the reactants are the things that are reacting. Out of these reactants, one of them will be the limiting reactant. And what does that actually mean? Well, the limiting reactant is the one that limits the reaction. The reason why, and this is a key definition, the reason why it limits a reaction is that it is used up first. If you're asked in an exam, what is a limiting reactant? You say it is used up first. The other reactant we describe as being in excess because there is so much of it. But the limiting reactant will affect how the reaction actually proceeds. Let's just say A is our limiting reactant and B is our reactant in excess. So why do limiting reactants have such an effect? Well, let's think about A, lots of particles of A, and lots of particles of B. Now B is in excess, which means there are so many of them, you don't have to worry too much. A, however, there are less of them. So when A and B collide to produce our products, C and D, because there are fewer of these particles, they will be used up first. But once those particles have reacted with some of those B's, the only thing you'll have left is reactant B. And at that point, the reaction will end. Now, there's a lot of relationships in science that you can look at. And one of those relationships is how the amount of product that's produced is actually influenced by the amount of limiting reactant. So we're looking at something called a directly proportional relationship. Now, in the case of a directly proportional relationship, we are looking at how the amount of products basically affects or is affected by the amount of limiting reactant. And it's quite a nice, simple relationship, but again, it comes up in questions quite often. When something's directly proportional, what you do to one, you do to the other. So in the case of a limiting reactant, let's say we doubled the amount of limiting reactant, what would happen to the product is that would be doubled as well. So if we went from, say, from 5 grams to 10 grams of limiting reactant, and when you reacted 5 grams, okay, the amount of product made was 15. If we double the amount of limiting reactant, you would expect to double the amount of product that could be possibly produced. The same thing goes if you half or if you multiply by 3. Let's say, for example, we half our amount of limiting reactant. We go from 5 grams and we take it down to 2.5 grams, 2.5. Exactly the same thing will happen to our product. So if we again say that 5 grams of reactant will produce 15 grams of product, the same thing has to happen. If you half your limiting reactant, you will also half, by dividing by 2, your amount of product. So that would give us 7.5 grams instead. Now this comes up in data questions generally. So you might be given information in a table format, something like this, and you might have your limiting reactant. In most questions it will be a particular example, but they will always say if it's limiting or not, and our product. Okay, let's say we're measuring all of this in grams. In the case of our limiting reactant, let's just say we have 1 gram reacting, then we have 2, then we have 4, and then we have 16. Generally, you'll be told one of the product amounts. So let's just say, for example, that 2 grams produces 10 grams of product once it has reacted. That's where you start to then look at the relationship between those values. So in the case of 2, if we go down to 1, what we're doing is we're dividing by 2. So if I divide my limiting reactant by 2, I have to do exactly the same thing to my product because of that directly proportional relationship. So it will go from 10 down to 5. If I go from 2 to 4 for my limiting reactant, I am multiplying by 2. So exactly the same thing has to happen. The amount of product that's produced also has to multiply by 2, giving me 20 grams for 4 grams of limiting reactant. If I go from 4 to 16, that is actually 4 times greater. So again, I'm multiplying that value for my limiting reactant by 4. In the case of our product, we also have to multiply by 4. So if the limiting reactant goes up 4 times from 4 to 16, our amount of product will also go up by 4 times from 20 to 80.